Okay, I would say go ahead.
Great. Well, hopefully we've got more than folks just here on Zoom. So I'm very happy to virtually welcome Professor Jaime Palter from the University of Rhode Island for our colloquium today. Bit of information about Jaime is that she did her about both her bachelor's and her PhD at Duke University, I'm guessing with Susan Lozier. Yep. And then from there, she went on as a postdoc at the Institute of Marine Sciences in Barcelona, and then Princeton University associated with GFDL. From there, she was an assistant professor at McGill, then moving to University of Rhode Island, where she has now an associate professor. Her research interests are mostly North Atlantic biogeochemistry and circulation and how the two interact. I first became aware of her work when I was working on my dissertation. I can very clearly remember seeing this new review paper on the Gulf Stream's impact on Europe. And I was trying to come up with a nice introduction where I'd gone through all of the North Atlantic, why North Atlantic oceanography matters. And this review paper was great. And I remember exactly where I was. And then if you fast forward a few years later to NCAR, and she shows up in my office because I had the office where the visiting scientists sat. And we had some great conversations, and I've enjoyed reading and following up on her and her group's research since then. So today's talk is called The Tail That Wags the Dog, Far-Reaching Consequences of Circulation Variability at the Tail of the Grand Banks. And I'm looking forward to hearing what she has to say. Take it away. Thanks.
Oh, thank you so much. That was such a nice introduction. And thanks for the invitation. I've also enjoyed your papers and getting to know you and others in this department. So I really appreciate that. And you already read the title, and I thought, I don't know how colloquial it is to say the tail that wags the dog. So I just wanted to point out that what I mean is when something important is controlled by something seemingly less important. And so I hope that gets everyone ready to think about this bathymetric feature, just an underwater plateau called the Grand Banks of Newfoundland, that I'm going to try to convince you, I think I've convinced myself anyway, has far-reaching consequences for oceanography and maybe climate. Okay, and I'll acknowledge while I'm here that a lot of the work was done by students and collaborators, and so I'll try to mention them at the right times. Before I get started, I want to plug three things. One is that I am hiring a postdoc to work on a funded project in the Labrador Sea. If you are at that career stage or know someone who is, please spread the word far and wide. It's a really exciting international project with a huge network of wonderful collaborators. And so if you're nearing that career stage or know someone that was, please reach out. GSO is also hiring a physical oceanographer at the assistant professor level. We have two deadlines the way it works, and we're in between the first and second deadline. I think there's about a week left if you're considering that. I'm not trying to poach anyone here. I'm looking at postdocs and later career students. And then finally, I would welcome interruptions during the talk, even if it takes me a bit longer to get through the slides. So just signs of life are always good. So without further ado, I wanted to take you to the North Atlantic, where there's a system of currents, which are often schematized in this very kind of simplistic way, with the warm waters of the Gulf Stream making their way across the equator and through the Florida Straits. Some of them recirculate in the subtropical gyre, and others go north of Iceland in the Greenland, Iceland, and Norwegian seas, and where they cool and become very dense, and others loop around into the Erminger and Labrador seas and become cold and dense as well. And that's shown in the blue colors, and then leave in the deep western boundary current along the western boundary of the North Atlantic. And this full system of currents has become known as the Atlantic Meridional Overturning Circulation. It transports a lot of heat out of the tropics and into the high northern latitudes. And it is known as a key player in our climate system. And this talk is not about all the ways it influences the climate system, but what might influence it, as well as some other oceanographic processes. So this is our simple schematic of what it looks like. But to an oceanographer who studies it, it is, every turn has complexity. The currents branch in many directions. There's obviously turbulence and ocean eddies. There's interactions of the warm and the cold branch. And I want to take you on a tour of some of that, but reducing that complexity to something we can really understand. I attribute most of the beautiful schematics and figures to my former student, Dr. Afonso Gonçalves Neto, who has taken a postdoc back in his hometown of Florianópolis, Brazil. He's a great science communicator and put together most of the beautiful parts of the talk come from him and others. So I owe him a lot of credit. I'll be talking about two of his papers. One was published in 2021 in Nature Communications, Earth and Environment. And the second is just about ready for submission. And so without further ado, the motivation, I want to start, of course, with the motivation for the first part of his talk was not actually the Amoc, although you'll see how it comes in at the end. It was the fact that the Northeast Atlantic Shelf is one of the fastest warming regions in the global ocean. In the last 10 to 15 years, it's been warming faster than 99% of the rest of the ocean, as shown by Pershing et al. In 2015. With that warming has come all kinds of consequences. Lobsters moved out of Rhode Island, the Rhode Island Sound, where I am in Narragansett Bay, and into Maine, enriching the lobster fishery there and depleting the local one where I am. A counterintuitive consequence is that even as mercury concentrations in the seawater of the Northeast Atlantic Shelf declined, because we've cleaned up our act in terms of environmental protection, the mercury concentration in tuna increased. And that's because a tuna in a warmer water has metabolic changes that has it cycling those toxins more quickly, as shown by Amina Shardup in 2020. The Atlantic right whale, of which there are only about 350 living individuals that we know of, shifted its main foraging habitat into the Gulf of St. Lawrence over here, where it was more likely to be hit by ship strikes or entangled in fishing gear. So there's a lot of consequences to these physical oceanographic changes. And so we wanted to figure out what was behind them. Why was the water warming so fast? And if they were predictable, to help managers and decision makers anticipate them and act. And so this is just a time series of the temperature in this region going back to 1950, just to illustrate the scale of the warming. After a cool period in the 1960s, we had warming and then somewhat stable temperatures until the 2000s, when we had a jump of nearly 2 degrees Celsius above the background mean. And now waters in this region are warmer than ever before recorded. The reason, so one way we can look at these changes is to think about ocean circulation. And we expect that some of that warmth is coming from the Gulf Stream, which takes this path along the red dotted line. It leaves the coast at Cape Hatteras and then takes this path out into the open ocean. And the Labrador current, which is very, very cold and fresh, takes a path out of the Labrador Sea, clinging to the slope around the Grand Banks. So this is the Grand Banks that I keep talking about. It's this underwater plateau. It's just a couple hundred meters deep. And the tail juts out here to the east, the southeast. We think that the Labrador current takes this path around the Grand Banks. And both of these currents can be observed from space using satellite altimetry. That's the sea surface height as observed from satellites. The Gulf Stream sits on a much higher sea surface height than the Labrador current. So if we thought that the Gulf Stream was coming closer to the tail of the Grand Banks, then we would see that as a shift in the sea surface height. And that was our starting hypothesis, that that warmth was coming from the Gulf Stream by blocking the Labrador current at the tail of the Grand Banks. And so we go to and look at the tail of the Grand Banks here, and we're going to plot sea surface height as a function of time from satellite altimetry. Here's another animation of that. The time series from 1993 to 2018, that's the length of the altimetry record at the time of writing. You know, we could extend it now a couple more years. It has averaged over this box. And it wiggles all around, but the most notable change is that after the summer of 2008, there was a shift to a higher sea surface height of nearly 10 centimeters higher. So in meteorology, this would be a big pressure change in the atmosphere, right? But we're looking at a change in sea surface height. And by formal change point analysis, it put that change at July 2008. And so if we plot the change in sea surface height as a map of the period from 2009 to 2018, minus the period from 1993 to 2007, we get this bullseye of very strong increase in sea surface height impinging on the bathymetry at what's called the tail of the Grand Banks here. And other regions of heightened sea surface height, which makes it look like the Gulf Stream or its associated eddies have shifted closer to the bathymetry. And what's great about altimetry is that you can take the gradient of that field to get the surface geostrophic velocity, which is what Afonso did next. And so here's the speed. We see the Gulf Stream coming out as schematized before along the from Hatteras and towards the Grand Banks, and the Labrador current coming out of the Labrador Sea and going in the other direction. And what we did is took the surface geostrophic velocity at the 500 meter isobath, projected it into along and across isobath components. And we're going to call that velocity field on the 500 meter isobath the Labrador current. And we're going to look at its continuity relative to the tail of the Grand Banks here. So what I'm going to show you is the correlation of the velocity at the tail of the Grand Banks with every other point along the 500 meter isobath. So it'll be a correlation of 1 at 0 lag with itself at the tail of the Grand Banks. And then we'll show that correlation at various lags and various positions along this isobath. And so this is going to be an animation that starts at negative lags, will show as negative numbers, and I'll show those correlations going through like this. The statistically significant correlations will show up in green and brown. So, and negative correlation, you barely see anything, but then we start to see a positive correlation moving through the system. And so this signals is that a velocity anomaly at the tail of the Grand Banks propagates along the slope with a lag of 2 months here, 3 months, 5 months, and it's outside the Gulf of Maine about 9 months later, and Cape Cod nearly a year later. And those are all statistically significant. So a velocity anomaly at the tail of the Grand Banks doesn't really come from very far upstream. It really originates there, but then it propagates all along the slope. Okay, and now keeping that propagation speed in mind, if we go back to the temperature data set that we started with, and think about that change in sea surface height initiated in 2008, we might expect to see a change in temperature thereafter, because remember, the source of the cold fresh water to the shelf is that Labrador current. If this region were to fill up with subtropical waters, of course, we'd have a warmer temperature. So in July 2008, we have no big change points, but then we're going to show the temperature change after a change point in the 150 meter temperature in this gridded EN4 product put together by the Met Office in the UK. So by May 2009, the Scotian Shelf has warmed by nearly 2 degrees Celsius. December 2009, it propagates into the Gulf of Maine. And by January 2010, a large-scale coordinated warming has filled the entire Gulf of Maine, 2 degrees Celsius as relative to before the shift. And so that was a very dramatic change that happened all during the altimetry record, which allowed us to see the shift in the position of the currents, or perhaps their eddies. If we look at the mean current, it's very hard to say because the Gulf Stream is extremely turbulent at this longitude. But it allowed us to have this multi-part linkage where we know that the velocity field anomaly, the velocity anomalies of the Labrador current propagate along the slope at a timescale consistent with the temperature change. And so the shift of the Gulf Stream over the tail of the Grand Banks has really set off a change in those waters. and gives us a lead time of predictability of over a year, which can be substantial for managers. And we've been in touch actually with some of the NOAA people that are interested in possibly using this as a metric to predict next year's temperatures. But what if we wanted to understand what happened not 15 years ago, but 50 years ago? Of course, that predates the satellite record. But what's amazing is that we can use temperature and salinity to reconstruct some of those changes going back much further. So here, I'm showing a temperature and salinity diagram. This is like the workhorse of physical oceanography. Salinity is on the x-axis, temperature is on the y-axis. And the reason that we love this is because temperature and salinity in the ocean interior only change very slowly by mixing. And so the temperature and salinity pair really tells you like the provenance of a parcel of ocean water. The Labrador current, again, is cold and fresh, shown in this blue trace, which is taken from this box here in the inset. The Gulf Stream is warm and salty, shown in this other trace from this red box here in the inset. And then everything in between is from the tail of the Grand Banks here in this black box. And it's separated by a decade. And so if the Grand Banks is more influenced by Labrador current water, we expect it to be cold and fresh. And by Gulf Stream water, we expect it to be warm and salty. And so just to draw your eye to the clusters of decades, we have 2010 by far being the warmest and saltiest, almost right along with the Gulf Stream. The 70s, 80s, 90s, and 2000s cluster somewhere in the middle. And then these early years, the 30s, 40s, 50s, and 60s, occupy a colder and fresher part of this parameter space. So what we'd infer from that is that the Gulf Stream over this longer time period shifted towards the tail of the Grand Banks, just as it did during the altimetry, albeit from a baseline with lesser Gulf Stream influence. Just for full disclosure, one of the decades, the 1990s, does cluster in these colder, fresher years. This was a decade without a lot of observations and also during a very extreme phase of the NAO. Both of those reasons could influence that. But just to be honest in how I'm displaying this, the earliest years cluster in cold and fresh. The warmest, saltiest years are our most recent years. The 90s are a little bit of a scramble. And then if we look at how these changes at the tail of the Grand Banks influenced the shelf region, we take that same region where we saw warming during the altimetry record, average the temperatures at 150 meters there, and look at their long time rate of change. Between 1930 and 1970, the annual mean 150 meter temperature fluctuated widely. Actually, there was quite a bit of variation, with the 1930s and 60s being the coldest, averaging about 7.3 and 7.7 degrees Celsius, separated by an intervening warmer period of about 8.5 degrees Celsius. But at the end of the 1960s, something remarkable happened. A rapid warming caused the mean annual shelf temperatures to exceed 9.5 degrees Celsius for the first time. And that state persisted with relatively little variation for 40 years, where the shelf temperatures from the 70s to the 2000s averaged 9 degrees Celsius. But in 2009, a second warming event, the one we've been talking about, raised the shelf temperature by another 1.6 degrees Celsius. And the subsurface temperatures after 2012 were warmer than ever previously recorded. Oh, and I meant to do that throughout. So from these observations, we concluded that changes in the along slope transport of the Labrador current originate at the tail of the Grand Banks and are highly coherent to about Cape Cod. When the Labrador current is blocked from rounding the tail of the Grand Banks, as we inferred from 2008, the Scotian Shelf and Gulf of Maine warm abruptly, with all of those serious consequences for fisheries and endangered species and things of that nature. The 2008 shift may have had a historical precedent in a shift towards warmer, saltier water at the tail of the Grand Banks and on the shelf, albeit under colder background conditions. And because the sea surface height at the tail of the Grand Banks precedes shelf temperature changes, by year, the work that Afonso led can provide predictability to decision makers, something of great interest. And so from there, we decided to test some of these ideas in a model, but I wanted to give a pause here to see if anyone online has a question that they want to ask before I move from observations to modeling.
John, I see your face. Do you have a question?
Yeah, this is really interesting, Jamie. You got to come and visit us another time. I'm just going to ask a question.
Yeah, sure.
Are these sea surface heights and temperature changes in a thermal wind balance?
They're probably not perfectly, but yes, that's a safe enough assumption.
Then how do they proceed? How does one precede the other then? Is the degree of imbalance, degree of thermal wind imbalance, does it erode over a period of time?
Oh, okay. The preceding is so what happens first is the sea surface height anomalies at the tail of the Grand Banks. That, the way I conceptualize this, and I think it'll be clear when I show all the model pieces, but the way I conceptualize this is that the Gulf Stream or its eddies spin in thermal wind balance, but these small scale features, the mesoscale, 100 kilometer or less, surge towards the bathymetry that blocks the Labrador current from coming around, and then starved of that cold, fresh water. My students always laugh at me because I don't know what to call it. We call it the tail of the Grand Banks, and then I don't know what to call I say it's the armpit of the Grand Banks.
Okay.
I want to show where I mean, but
The lee side?
Anyway.
With respect to the Labrador current, maybe?
Yeah, where the Scotian Shelf and Gulf of Maine are.
Okay.
Here, I'm not showing it well, fill up with the warm water. So sea surface height changes, it blocks the Labrador current, starved of the cold, fresh water that the shelf region fills up with the warmer, saltier Gulf Stream and subtropical waters.
And then that acts in concert with a specified lag as you showed. Okay, I get that now.
Yeah.
I think. Okay, thanks.
Yeah, no problem. Okay.
I see Evan appeared. Evan, do you have a question? We can't hear you.
Okay, can you hear me now? Yep. This is a kind of a basic circulation question, but I was just wondering if there was a reason that the Labrador current is sticking so much better to the bathymetry compared to the Gulf Stream.
Oh, that is a cool question. Basically, this is like a great oceanography question. The Gulf Stream is a western boundary current that relies on bottom friction to close its vorticity balance. I know the meteorology crowd will appreciate that. But at some point it leaves the western boundary and becomes like an inertial extension and goes off. And we call that the separated Gulf Stream. And it starts meandering wildly like a hose, if you held a garden hose and it's flapping around. And so it's just, we're at that part of the Gulf Stream. And then it does kind of reconnect with the western boundary. I think what's happening is it kind of reconnects with the western boundary because the bathymetry juts out so far into the basin, where the Labrador current doesn't kind of hit that turbulent inertial thing until it has to make the turn, that sharp westward turn around the tail of the Grand Banks. And at that point, it starts eddying too. And so these two eddying currents then collide. One is very, very warm and salty. One is very cold and fresh. And that's what I think is the tail wagging the dog of all these different things, the shelf warming, and as you'll see in a little bit, the Atlantic Meridional overturning circulation too.
Gotcha. Thank you. I feel like I need to watch animations of these things happening for a couple hours.
I have something. Okay, that makes me feel like if there's another urgent question, I can do it, but it makes me feel like I should go to, I have an animation coming that might help. It might not, but we can try.
Hannah, do you want to ask a question now or wait till the end and we'll take a look at that?
I think it's just real quick, hopefully.
Okay.
I was just wondering, so based on your TS diagram, how much of that do you know is potentially related to just the Labrador current warming, or is it at all?
It's just way too much.
It seems like that to me too.
In fact, I wish I could flip through these easier. If you look, all of those temperature and salinity curves, those of the different decades, join at the bottom. The Labrador seawater actually hasn't really changed in its temperature and salinity. And the Labrador current is made of Labrador seawater plus a bit of a seasonal thermocline from like subpolar summer.
Yeah.
So it's just way too much warming for it to be like, and it's just much
Any
faster and much too
significant
much.
amount.
Yeah,
Yeah,
so
that's
it
kind of
really
what
has
I
to be a water
figured.
map. Yeah.
That's what I figured. Cool. Thank you.
Okay. Okay. So this is great. I love it. I love knowing that I'm not alone here. Okay. So I'll keep going and hopefully it'll clear up some questions. So Afonso next turned to a model called HICOM, which I'll introduce in a second, to take a Lagrangian perspective. So look at water parcels as they move through the system, which I think was really instructive to us to understand more about what was happening. So HICOM is an ocean model forced by atmospheric reanalysis. And this particular one was run at 1/10 of a degree without assimilation. So it's a free running ocean model. It has been, the reason we chose it is because it has been like really, really validated against observations. And I'll just show 3 examples, although there are more. The currents in the Labrador Sea shown from observations from moorings on the left and the model on the right match closely. This very hard to model region, what's called at the mid-Atlantic ridge, called the Charlie Gibbs fracture zone. Observations at the top from moorings, model at the bottom. It doesn't look perfect, but what it's showing here is like an emergent property of this really complicated flow, with the North Atlantic current is an extension of the Gulf Stream going east. And beneath it, so this east here at the top, and beneath it, the Iceland-Scotland overflow water going west. And that is a very hard thing for models to get right. So, and then most important for our purposes are the observations of currents at the eastern Grand Banks, shown from moorings here, and the model here. And so it gets the Gulf Stream offshore in the right position, about the right strength, and the Labrador and deep western boundary currents here right along the shelf. So that's really key. Models have not been able to do this very well until the last several years, like 5 to 10 years, when they were getting them a little bit better. And so what Afonso did was release Lagrangian particles just upstream of the tail of the Grand Banks in layer 19 of the model. It's a layer model, which means it represents the layers of the ocean by their density. And that layer is right at the top of the denser water, so just below the seasonal thermocline. And we're going to trace where they go. And so here's an animation that might, I'm hoping, help Evan and others. A Labrador current particle that deployed at that location makes its way along the slope. And it gets, entrained in eddies, but it kind of makes its way, as you kind of expect, along the deep western boundary, or the Labrador current on the slope area. And then, I don't know why that looks so jumpy, but then we have others that get entrained into the Gulf Stream. And instead of making that western turn or southwestern turn, they move off to the east. And we're going to call those North Atlantic current particles. And we ran these for thousands and thousands of particles, and the whole region just fills up. And you can look at all the spaghetti, but it helps to make sense of it if you look at a probability density function of where the particles end up, which is this. And I promise it will help make sense of it in a minute. So all the parcels are deployed here, and they spread in all directions. These are just the endpoints, like a scatter shot of the endpoints. And beneath it is the probability that the parcel passed through one of these areas. So 100% are at the starting place, although the color bar saturates. And then you can see something like 10% make it to this white ring here. But what's really interesting is to think about the variability in this field. So in 2004, particles deployed here go in all directions. Some go east, some go west. But in 2008, the ones going east are just gone. 2008 being the familiar year when we have that big sea surface height change at the tail of the Grand Banks. And remember, this model doesn't assimilate data in the ocean, but it is forced by a realistic atmospheric reanalysis product. If we subtract the probability distribution of 2008 minus 2004, we can see very clearly that 2004 had much greater Labrador current connectivity to this region off the Scotian Shelf and Gulf of Maine. And then to show it in the spaghetti diagram, this is what it looked like in 2004, which we ended up calling the valve open period, because it's like the valve of Labrador current to this slope area was open. 4% of the particles made it region. 34% did not, or were called North Atlantic particles. You might be asking, what are the others? The other percent, they just kind of recirculated locally. But in 2008, the valve was entirely closed. 0.3% of the particles managed to make that westward turn. 75% became NAC particles. Okay. So what changed between 2008 and 2004 to close the valve at the tail of the Grand Banks? We already know that there was this big sea surface height anomaly, but we wanted to put this in this oceanographic context with a 2-layer conceptual model. So the idea is that we have a top layer that sits above the picnic line, the stratified layer, and a bottom layer that's between that, the stratification and the sloping bathymetry of the ocean bottom. If we put a parcel in that bottom layer, then it wants to conserve its potential thickness. It wants to stay in a layer of constant thickness normalized by the Coriolis parameter. And so the idea is that when the Gulf Stream or an eddy, a Gulf Stream eddy, comes towards the bathymetry, it squashes that lower layer. The sea surface is higher, the picnic line is lower, and that lower layer gets squashed. And for the parcel to stay in its at its constant potential thickness, it wants to migrate offshore to deeper water, because for conservation of potential vorticity or equivalently thickness, as the layer gets squashed, it needs to find deeper water to stay at its constant layer. And likewise, if the Gulf Stream moves offshore and the lower layer is stretched with the Labrador current, then that water will cling more towards the sloping sea surface and be more adept at making that right-hand turn at the tail of the Grand Banks. And so to check this out, we look at the potential thickness. So this is a map of this. It looks just like the bathymetry because the stratification doesn't change by thousands of meters. So it looks like the bathymetry, but it's really the combination of the depth of the picnic line and the bottom bathymetry. And the time series of the potential thickness anomaly shown in black in the tail of the Grand Banks box can vary by 300 meters. And that's enough, we think, to cause those Labrador current parcels to leave the slope and get entrained, where they're very easily entrained into the Gulf Stream and advected to the east. And so in black, we have the potential thickness anomalies showing lots of wiggles, but a trend towards very much more negative potential thickness anomalies. That's a high sea surface height, a squashed lower layer. And the blue lines are the percentage of particles that make that right-hand turn to the slope. And obviously these are anti-correlated, especially in 2008, 2010, we have the biggest anomalies, negative anomalies of potential thickness and no particles getting through. And so the conclusions from I'm checking the time here, from the Lagrangian experiments were that, again, confirmed this idea that the impingement of Gulf Stream waters at the tail of the Grand Banks, which are signaled by a deepened picnic line, can cut off the direct advective connectivity of the Labrador current to the Scotian slope. And a 2-layer conceptual model, the one I showed you, really skillfully allows us to, we have a mental framework now to link the variability that we infer from sea surface height in the observational record to the Labrador current connectivity or its lack of connectivity, that discontinuity. Okay, and then trying to build dramatic tension here, because something that occurred to me as Afonso was wrapping up, but is if the 2-layer model is useful, could we infer that the entire deep western boundary current that carries the deep limb of the Atlantic Meridional overturning circulation would also be disrupted in the same way? So far, the layer 19 results that I showed you are not super deep. They're not really, they're above Labrador seawater. They're above that deep limb of the Amoc, because we were really interested in what makes it onto the shelf. We were interested in that shelf warming and giving predictability to managers doing fisheries. But then as I got deeper into it, I thought, if that Labrador current is cutoff could also the deep limb of the Atlantic Meridional overturning circulation. And so we continued doing this work now with my new student, whose name is Farah Hanifa. And I only have a group picture of her. This is my wonderful group at present. And that's Farah on the left. She's a Fulbright student who's been working with the HICOM output to understand the links of Afonso's work with the Amoc. And so we have this really interesting region where the Gulf Stream is side by side and interacting with the deep western boundary current. That is, the shallow limb of the Amoc and the deep limb of the Amoc are crowded into this one box at the tail of the Grand Banks and interacting. So how does that manifest as variability in the Amoc or changes? And so to just give a mathematical definition of Amoc, what it is the integral of the north-south or meridional velocity from the western boundary of the basin to the eastern boundary of the basin, and from top to bottom. And it's important to do that vertical integral in density space because sometimes these currents are actually at the same depth level, but at very different densities. When the you can picture that as the Labrador current might be very near the surface, and the Gulf Stream might be very near the surface, but they're in very different densities. So that's the definition of the Amoc. And here's a trace of the Amoc versus density at 45 north. And so if we accumulate northward flow from the surface, that's that vertical integral towards the bottom, we get to some maximum here. And that's what's typically reported as the Amoc, the maximum meridional transport integrated from top to bottom of about 15 sphere drips or 15 million cubic meters per second. And because what goes north must come south for conservation of volume, otherwise we have wild sea level changes, the flow southward matches the flow northward so that we have zero net volume transport across a line of latitude. And so we typically Amoc is reported as this positive value, but you can think of the Amoc as north and south having equal volume transports, and that becomes important. So at 45 north, I wanted to look at the variability in the dense Amoc transport and compare it to the Amoc transport. Okay, this gets a little bit complicated, so I'm just going to write it out. The dense transport is anything below that maximum. Let me go back 1 second. So the dense transport is shown in blue here. It's anything below this maximum. So it's like negative 15 sphere drips in this case. Okay. But also, so that would be the dense transport integrated all the way from west to east, and that would be the Amoc. But we can also look at the dense transport integrated to any longitude. And what I'm going to show you is the correlation of the dense transport at each longitude correlated with the Amoc transport, so the full dense transport all the way across the basin. And so these have to be one, so that's in blue. Red is the shallow transport, which I'll touch on in a second. These have to be one at the eastern boundary because that's the same number. It's Amoc correlated with itself. But going now west across the basin, the correlations decline as expected because there's all kinds of variability in the transport that will reduce the correlation with the full Amoc. Except look what happens when we get back to the Grand Banks. We have correlations of 0.8 in the dense water transport. More than about 70% of the variance of the low pass filtered, 18-month low pass filtered Amoc is captured by the dense water transport along the Grand Banks. So this, I think, has huge implications for if this holds true in nature and not just in the model of what you'd monitor if you wanted to monitor low frequency fluctuations in Amoc. You get most of it just within a few hundred kilometers of Newfoundland. The same cannot be said of the shallow branch. You need to integrate the shallow component of the Amoc clear across the basin to about 10 west, all the way to here, to get the same degree of correlation with the full Amoc transport. And just to visually show that, Farah has just plotted here the full Amoc transport in blue. and the transport just to 45 west, right along the Grand Banks in black. So these are very highly correlated in high com. What's great about this is it also has an explanatory value for a long noted correlation between shelf temperatures and Amoc. So I just told you the shelf temperatures, I gave you this whole, first 25 minutes of the talk of why changes at the tail of the Grand Banks change the temperature of the Scotian Shelf. Well, that has already been noted to be correlated with Amoc, both in observations, and which we have precious few of, only 10, in this case 10 years. It's now been about 15 years, but also in a different model, a free running climate model that's very different from HICOM in all sorts of ways, but does a pretty good job resolving the currents, is very strongly anti-correlated. When Amoc is low, here in black, the shelf is warm. When Amoc is high, the shelf is cold, as noted by Saba et al. In 2016. And so that's the GFDL model. And now we see the same thing in this HICOM model. High Amoc, cold shelf, warm shelf, low Amoc, it's hidden behind your pictures, low Amoc, high shelf temperatures. And so I'm going to end with the newest piece. So this is really hot off the MATLAB, not published yet. But I think that using this framework, we can start to address what Robbins and Meyer, writing for the Atlantic magazine, said in 2018 was a real debate in climate science, which is whether the Amoc will shut down in the future. And I would add to that, we have long been debating whether it's already started to slow down. It's a hot topic that has been widely debated. And so I want to just end by thinking about, do we know if the Amoc has already slowed in this framework? And this is personal for me. So I started by showing you Afonso's work. Now I'm going to show you some work from Tom Rossby, who's my colleague at URI and also my academic great-grandfather. So he was Susan's advisor's advisor. That's my advisor. And so this just unites 5 generations of oceanography, which I absolutely love. And Tom has been, a tremendous mentor and collaborator at University of Rhode Island. So I just want to honor that. So he also has an expansive memory going back many decades into observational oceanography. And what he realized was that Columbus Island collected really high quality sections from Long Island to Bermuda dating back to the 1930s, shown here in pink. Hydrography at Bermuda has been observed since the 1950s when Henry Stommel, Tom's advisor, started the Hydrostation S. And this tradition of making observations between the slope, which he takes this polygon at the slope, and Bermuda has a long history and many other observations, but I'm just showing here, or he's showing really the lined up, the Iselin sections from the 30s and line W, which was a sustained program from the 2000s in blue. And there's lots of other data that went into this analysis that is not shown here. He added to it the innovation that he has 25 years of observations of the Gulf Stream from a merchant vessel that takes goods from New Jersey to Bermuda and trash from Bermuda to New Jersey. Tom with collaborators outfitted that ship with an ADCP, a current meter, to get Gulf Stream measurements twice a week for 25 years, which is really remarkable. And so with that, he also he knows the depth of no motion, which allows him to calculate with geostrophy. So we've been collaborating on this. So we're going to take these observations on the slope and observations of Bermuda to perform geostrophy and find the transport between these two places and look at changes over time from the 1930s onward. It's important to note that the temperature changes I already showed you are really, again, unique in the ocean. They're warming much faster than elsewhere. That warming is accompanied by a small salinity change, but overall it's a density decrease because the temperature dominates the density. Whereas at Bermuda, it's warmed a bit, but so much slower than on the slope. And so what that means is if you take the potential energy anomaly at the slope, we have a strong trend, and at Bermuda, a very weak trend. The same can be said for if we repeat this at Africa, which he has done, but I haven't included the figures just for brevity. And so when we put this all together to get a direct observational measure of the Amoc using geostrophy from the 1930s and just putting a trend line through it, we find a trend of 2.5 sphere drip decline, 2.5 million cubic meters per second decline per century, plus or minus 1.2. And that, I think, is the first direct observational evidence we have of that, or the most direct. It amazingly matches some inferred geostrophy changes in the Florida current from tide gauges. This has been shifted down by 10 sphere drips because that includes some wind-driven stuff put together by Chris Pikuch in 2020. By a very independent method, it matches approximately the trend from Cesar et al. In 2018, which was like a totally different method. It maybe even be a little bit coincidental, but it looks at temperature anomalies as a proxy. But what is stable during this time, interestingly, is the outflow from the Nordic seas. So Tom thinks, and I agree with him, that this really is a signal of a change in the Labrador seawater or an Erminger seawater, and so the intermediate depths, not the deepest North Atlantic deep water. And so, okay, with that, thank you for your patience. Hope that wasn't too long. So I'll leave you with this cute picture of the dog wagging its tail, or really the tail wagging the dog. I've shown you that small changes, actually difficult for people have looked at the Gulf Stream and its changes, and there's really not a big shift in the Gulf Stream latitude upstream of the Grand Banks, but these really subtle changes right near the bathymetry lead temperature changes on the Scotian Shelf and off of New England by a year. The shelf temperature changes have this big change point. The shelf temperature has a big change point after 2008, after the increased impingement of the Gulf Stream. The Lagrangian experiments really helped us explain why, using this two-layer conceptual model. And when we think about that two-layer conceptual model, it gets us thinking that maybe it influences the entire deep branch of the Amoc, which turns out to have some corroborating evidence from the model experiment and also from the longest records of hydrography that we have. And I'll leave those conclusions up and happy to take more questions if there's time.
That was super cool. I'm going to give you a virtual round of applause. I'm the only way to hear you. Or you the only way to see me. Do we have any questions first from any students?
I have a few questions, but I'll try to keep it short. My first question is there an equivalent to anything like this in the Pacific Ocean? Like, can you see if there's another tail and see something similar going on? I know that there's not an equivalent to Amoc, but would you be able to see some sort of western boundary and a similar variability?
I think that is such an interesting question. And I don't think there's an equivalent bathymetric feature that juts out like that. And so the Kuroshio, which is the kind of the Gulf Stream equivalent, the western boundary current of the Pacific, it has decadal variability, but it seems to be set off by these Rossby waves that propagate across the Pacific, and the Pacific's so wide that it creates these like this very low frequency variability at decadal timescales. And I think that is what I understand to be a big source of decadal variability, and it manifests in how wiggly it is, how meandering, and how many eddies it sheds. But I don't know of anything like this where there's like a strong variability or trend in the interaction of the Kuroshio with the Oashio, which is kind of like the Labrador current in the other direction. But I actually think it would be a cool thing to look through, but I don't exactly know the answer, but to my knowledge, no, there isn't anything quite like this. Yeah.
Cool. And then my second question is, so you're starting your tracers right at the Grand Banks, right? Mm-hmm. And so I guess what I was thinking is, if you have such great variability in the picnic line depth, how do you know that you're not just putting a tracer in the Gulf Stream as opposed to in the Labrador current? Like, if the mixed layer gets so low and you're starting the tracer there, then it might already be from the Gulf Stream.
I think actually you're right to a certain degree. So I'm used to being able to, I have some extra slides. Let me just see. Okay. This is the launch location of where we put it. And all the way on the right is the velocity. And so I don't love the way Alfonso rotated these, because now the red colors are going south, so that the positive numbers are in the Labrador current.
Okay.
And so he deployed those particles everywhere on this thin slice along this section. And it looks like it's southward everywhere, but actually when you get to the extreme right-hand side of the section here, it's like a sticky pointer, I don't know. When you get to the extreme right-hand side, I can't get the pointer over there, it is slightly northward. So those particles on the extreme right-hand side of this, it's all rotated. So it's mostly east, but not exactly east. Those go north every time. Those are always in the Gulf Stream, so you're totally right. And the other thing that really surprised us was that we deployed the particles also in the mean flow, the non-eddying flow, to see if it was, we thought there'd be much more connectivity without the eddies, basically, because we thought it was Gulf Stream eddies cutting it off. But when we did that, actually fewer particles get through without the eddies. And it's because the Labrador current is also eddying, and you need the Labrador current eddies to get around. But then on top of that, sorry, I'm going a lot of layers, but on top of that, the mean flow in the 2004 period, like the open valve periods, has connectivity, and the mean flow in the closed valve periods doesn't. So it's actually like there's enough Gulf Stream eddies, or the Gulf Stream itself, or something about it cuts off that flow, even when you average over the eddy period. And I don't know what else to say about that, but that took us a little bit by surprise. And so I think you have the right instinct. Some of this section has Gulf Stream in it. And so the particles deployed most to the east just always go north. The particles deployed most to the slope side can go either direction. When the valve is open, many more of them, like over 30%, make the turn. And when the valve is closed, none do, basically.
Is this graphic a like a long-term mean?
This is the average over, I think, the whole simulation.
It would be really interesting to see this graphic in 2004 and 2008 to see if like that always northward part is a lot larger.
That's a good, yeah, we should do that. That's a good idea. I have something, can I get here? This is now zoomed way out. And so this is from Farah's work. And so what you were just looking at was this tiny bit here, right on the slope. So, and now the colors have been reversed, just not to make you crazy, but so the blue is now the Labrador current, and that's coming out of the screen, right? Like going south. And you can see there's like bits of the Gulf Stream and the deep Western boundary current is here. When the Amoc is strong, this whole thing is negative or southward, and the Gulf Stream's here. When the Amoc is weak, and likewise the Labrador current weak, you have this slug of northward flow right up against the slope, and it just cuts off. It just creates strong discontinuity and a weakening of the Amoc. That I wish it was a more crisp, like clean thing, but I think there's it, and you get the sense, right, that it's an eddy. Or a standing eddy or something, right? And that you have some kind of anticyclonic circulation here. But that's how far we've gotten so far with that piece.
This is really interesting. Thanks,
thanks
for the talk.
Thank you.
John, I think you have a question.
Yeah, thank you, Jamie, for a really great talk. I had a question, and I'm sorry that it's going to be naive, so I apologize for that, but it strikes me that the Gulf Stream's position relative to the tail plays a role in this whole story, whether it really brushes up against it or it's well to the east or southeast. And so variability in the position of the Gulf Stream is an issue. Is that correct?
Yes, but
And
as my friend and colleague Kathy Donahue likes to say, what really is the Gulf Stream here? And maybe that actually it's really like a whole bunch of eddies. It's so broken up.
By the time it's at this longitude, okay.
Yeah.
Because then the rest of my question falls away. I was thinking of it as sort of a jet, and I'm wondering if the jet is having some of these eddy characteristics as a function of imposed forcings or internal variability. And is there a way to separate the two? But maybe the question doesn't apply at this longitude, as you just maybe suggested.
I don't, if it does apply, I don't know the answer. So it, where around here is about 50, I don't have a lot of longitudes on here. It's about 55 west.
Mhm.
And really it's not jet-like after about 65 west.
Okay, okay.
And so it's just, I actually, I wish I could give a talk about this already, but it's too fresh. We have currently 3 sail drones out there. And one of them is at 65 and one of them is at 55. And it's like, we're trying to send them across the Gulf Stream, but there's like no Gulf Stream. It's just,
Okay.
it's even at 65, it's more of a Gulf Stream, but it still breaks into eddies and it's so meandering. It's really hard to know what's happening.
Yeah, okay, okay. And just a quick follow-up. Can anybody run a model without the Grand Banks in it? See what happens?
I know, that's what I said that to Elizabeth. I was like, what if we just shaved that off and set it, because it is a bit presumptuous of me to think it's the bathymetry. And I don't know that that's true. You know, it could be, I wonder if it could happen in any case, even if it was flat. And I think that would be an interesting, that's like such a perfect model manipulation that you could do, is just shave it right off and see what happens. Because, so Elizabeth's been involved in amazing work looking at the strength of the Labrador current way upstream of this region. And actually it's not framed in that way, but it looks like the buoyancy forcing, the heat loss in the Labrador Sea creates thickness anomalies that themselves propagate out. And maybe the bathymetry, I just did this whole thing about wagging the tail, but, or the tail wagging the dog, but maybe the bathymetry is secondary to these very strong pulses of thick Labrador seawater that set the thickness anomalies. So there could be a push mechanism where you thicken the Labrador seawater layer. And as that anomaly moves through the system, that could preclude the Gulf Stream from coming close enough to block it. So I think I would love to see a model experiment like that.
Well, thanks for a great talk. It was fantastically interesting.
Oh, thank you.
I
Wow,
think-
you're very generous. Thank you.
I think we can talk about that experiment
Yeah.
tomorrow, but it looks like Fung has a talk or question.
Yeah, thank you, Jimmy. Wonderful talk. I really like the idea that the tail of the Grand Banks, can control the whole Amoc. This will be very useful. That means we don't have to measure the whole width of the Atlantic Ocean to monitor Amoc. I'm just wondering, can you tell us like how the property of the Grand Banks can slow down the Amoc? Is that due to the warming of the seawater there, or it's due to some response of the Gulf Stream to the global warming?
Okay, okay, I'm gonna first make the caveat that there's part of this that's really model driven, and the Amoc piece is very model driven. So with the caveat that I don't know if this will hold in nature, that monitoring a narrow region gives you information about the whole region. I just don't want to way overstate the case. And also, I don't know that the tail controls everything. Now I'm getting nervous that I way overdid this, but so much that monitoring there gives you lead time for understanding what's going to happen downstream from the point of view of the Labrador current. Okay, so then the question is why? Why have we seen this shift? And I don't have an answer for that. Although I will say that the very first project that I did that touched on this used the GFDL model. And what was interesting in that is this shift only happened in the model simulation with a doubling of CO2 in the atmosphere, like the anthropogenic radiative forcing of increasing greenhouse gas in the atmosphere. It did not happen without it. One model, this is not a large ensemble. This is not like bulletproof, this is not proof for sure, but I would guess that anthropogenic forcing has a role to play in, that would be my best guess, would be that anthropogenic forcing has a role to play in whatever's happening to make the Gulf Stream get closer to that bathymetry. And I think that there's evidence of that in other work too, like Laura Zana at NYU has done really cool work on some of those, of using large ensembles to look at temperature anomalies and how those are anthropogenically forced, that I think might have something to do with this. But at this point, I'm really hand waving.
Thank you, Jimmy.
Yeah, thank you.
Larissa's got her hand up.
Yeah, I think that answered my question a little bit, but I was going to ask what role the atmosphere plays in all of this, essentially. So if any.
Yeah, Tom Rossby and I have talked about this a bit, because the atmosphere has a huge role but in multiple ways. And so it's so hard to know. And it responds to the changes because this sets up temperature anomalies at the sea surface, like where the Gulf Stream front is. So the atmosphere is really important for extracting heat from the Labrador Sea, which could set off this chain of events and thickening the Labrador seawater layer, like in the work that Elizabeth's been involved in, and maybe pushing the Gulf Stream further from the bathymetry. But it also has a role in setting like where the zero wind stress curl line is, which kind of sets the position of the Gulf Stream. And the NAO can create a more southerly route or a northerly route. So there's the wind force, the buoyancy force, and the interaction between them, and then the feedbacks on the atmosphere. So that's all to say that that's a level of complexity that I don't know the answer to. And I think it will be very hard to tease apart, actually. So yeah, good question for someone to look at in the future.
Okay. Thank you.
So with that, I want to be cognizant of everyone's time. We're at 4:30. I'll just hold my questions till meeting with Jamie tomorrow. But thank you again so much for the great talk. That was super cool. Another round of applause, and we will see you all next week.
Thanks. I look forward to the